Hi, welcome back to my channel. So this is another video about the QRPLabs amplifier, 10-watt HF amplifier. And in this video I'm going to verify its gain performances across the spectrum from 1.8 MHz to 30 MHz and its linearity. So I'm going to consider the original amplifier, so as it comes in the kit, so without the modification I did in one of my previous videos, basically to improve the input impedance. Okay, so I'm just going to verify the original design because I guess this can be of interest to more people. Okay, so at the moment I have my signal generator sweeping, as you can see in the spectrum analyzer here, but more clearly here, sweeping the spectrum from 1.8 MHz to 30 MHz and emitting a signal at 10 dBm. So I've set up basically the spectrum, the signal from the signal generator is going through this 30 dB attenuator and this 20 dB attenuator. I've checked and the actual total attenuation is more about 49, not 50, okay? So I have instructed the spectrum analyzer to consider this. So when you see the result here, it's already basically compensating for the 49 attenuation happening here. So you see here the result of basically the signal generator before going into the amplifier. And indeed, as you would expect, it's just sweeping precisely at plus 10 dBm across the spectrum. So the reference at the very top is 50 dBm. The line that you see there is 40 dBm, which means 10 watts. And then we have 10 dB for each scale. So 40, 30, 20, and indeed we are at 10. Okay, so now I'm going to basically connect this stimulus, this 10 dB stimulus going to from the signal generator, and see what happens after the amplification. So instead of a battery, this time I'm using this power supply here. It's not really the best. I think 2 amps is about the limit this can go, but anyway, it's more handy than a battery, so I will use this in this video. Okay, so let me stop the signal generator and I'm going to connect the signal generator to the input of the amplifier here. And the output of the amplifier to this chain of attenuators. So there. Alright, I'm going to power on the amplifier and it's done. It's drawing at the moment 340. It's growing so that the amperage grows with the temperature, but we are now 350 milliampere, which is the perfect. I mean, this is what is suggested in the instruction manual. And so now I'm going to start the signal, and we will see what happens. So as you can see, with this stimulus, we are getting this response. And so let me actually take the trace, just take the maximum so we can see what happens. Right, so this is the gain performance of the amplifier. Actually, it's the signal generator now is stopping at 28 MHz, so let me actually set 30 MHz so we can see what happens at the end. That's right. And so you see that, so let me take the marker. At 1.8 MHz, which is the beginning of the spectrum, we are getting 35 dBm, so an amplification of about 25 dB. This grows here, I guess, is the maximum. Around 11 MHz, we are amplifying 27.7 dB, and then it goes down 25 dB of amplification up to 24. Okay, so I would say that the amplification ranges from 24 to 27 dB across the spectrum, which is, we can call it therefore a 25 or 26 dB plus or minus 2, I would say. Okay, so the amplification that I have measures is more or less like this, okay, across the spectrum. So in fact we measure 27.7 as the maximum, right, and so this was at 11 megahertz, and a minimum of about 24 dB at 30 megahertz. So this is what we measure. So let's take this as the average, and indeed this is the expected amplification of the amplifier. So this is up to specification. And okay, so let's see where we can go by increasing the amplitude. So at the moment the amplitude is 10 dBm. I'm going to increase it by 1 dB. Let's see what happens. Okay, the sweep time at the moment is 5 seconds. Let me put it 2 seconds, so it's a bit faster. Okay, so we have a better update. So let's follow. Now we are at the stimulus is as before 10 dBm, and at 14 megahertz we are getting our 37.55, so 27.5 of amplification. And now I will start increasing the stimulus by 1 dB. And therefore, let's see if it increases there. Yeah, now we have a 38 point something. Now let me move to 12 dB. .8. Let me go to 14 directly, because 14 plus 26 should be 40, and we should be there, right? So let me actually remove the hold max, because yeah, as you can see here it's more dynamic, we can see. So basically we are getting 10 watts at lower frequencies and dropping a bit higher frequencies. Let me repeat the hold max. Right, so we have this curve, right? So we can basically have 20 watts basically across all the spectrum, and it's dropping a little bit, 3 dB more. So here we only have half a watt, 37 dB is only, sorry, 5 watts. Okay, so this is the performance. And let me have a look if I increase the input, let's say, to 17 dBm. Let me see here. So at some points we are going above the 10 watts. Let's see where, like here at our 40 megahertz, and we are getting 41.42 dBm. Let me try 20 dBm. I reached the maximum of my signal generator. Anyway, here I guess we are probably around 12, 13 watts, something like that. Okay, so let me reduce the input. Let's go back to 10 dBm. So 10 dBm, and let me clear the trace. Okay, so we are at the original stimulus. Now, so basically the conclusion is that yes, the amplification is about 26 dB, plus or minus 2, I would say. And indeed we can achieve our 10 watts. So let's fix, actually let's stop the sweep, and let me fix now a specific frequency, like 14 megahertz. That's the frequency I care the most. Okay, so now we get the signal. It is the moment 36.7, I guess. So let me increase slightly until we get to 40 dBm as an output, and it's there. So with an input of 15 dBm, I'm getting an output of 40 dBm. Okay, so the actual 10 watts at I'm writing like here at 14 megahertz is achieved at plus 15 dBm. Okay, so this is the value that we are looking right now. Okay, so now I'm going to go for another type of test, so basically linearity. And for that, so at the moment I have this 14 megahertz signal. Let me zoom in it. So let me center it on the screen. Let me reduce the span, let's say, to 100 kilohertz. So we are a bit off here, so let me move back the frequency where we're supposed to be. We should find a signal at 14 megahertz. Here it is. Okay, perfect. So our signal at 14 megahertz. Right. Right, so let me center it perfectly. 14 megahertz. Okay, now what I'm going to do is generate another sine wave 1 kilohertz away from this main carrier. So let me do that. So this is a possibility of this signal generator. So basically it's done this way. So let me zoom in more. So let's this with a span of 10 kilohertz, and so let's see the result. Okay, so this is the result. So let's go back to the signal here. I'm going to now to reduce the input power to let's say minus 5 dBm, so something very weak. So as you can see here, these little tones that are not present really at the signal generator, they are generated by the amplifier, are pretty small when the input is low at minus 5 dBm right now. But as you can see, if I mount it up, they start to grow. And now we are at 0 dBm. And yeah, so I think an acceptable performance is if these third intermodulation products, as they are called, basically these side tones are generated by the intermodulation of the two main tones, okay? And there are actually many other tones that at the moment are invisible, but they will become visible when we increase the power, that are further modulation, so they are called further higher order products, basically. But these that we see here are exactly 1 kilohertz away from the main side tones, main tones, and are the third order products. And so let's increase the power up to when we get basically, okay, so this is the maximum I can get. Okay, so 11 dBm for tone. Right, so let me have a look at the peak here. The peak says 35 dBm. Okay, and so the third order modulation product is at 17. So it's basically 18 dB down compared to the main carrier. As you can see now, we have many more intermodulation product beside the third. I mean, many higher order. But still, the third order, which is the most significant, is about 20 dB down. So I would say that this is okay. These higher order undesired product grow faster than the main carrier here. And so, well, basically, let's take note of this, okay? So when the, let's say, let's put a 5 dBm input there. So at 5 dBm, third order is 10 dBm. So I just took note of this fact that when the input from my signal generator is 5 dBm, this third order undesired product is, as you can see, at about 10 dBm, while the main carrier is at 31. First is 31. Right, so with this information we can compute some numbers. Okay, so with the data that we have collected, I have depicted here a small graph. So here we have basically we have dBs for input. So the x-axis is the input, the power of the input rather, and here is the output on the y-axis, and we are talking about these 14 megahertz. So I've modeled the amplifier as a function that basically takes an input and adds 28, because we saw that this is what is the behavior at you know, of the amplifier when the input is not too high. Okay, so for example, when the input is 0 dBm, we get 28 dBm of output. Similarly, when the input is minus 28 dBm, we get 0 dBm of output. Okay, so we can model the amplifier by this curve. And here instead I've modeled with this 3x minus 4 the growth of this intermodulation product. So as you can see, at 5 dBm, where the input that is generated now, we are seeing that the third order component is at about 10 dBm here. So let me now reduce the input to 0 dBm. Right now it is 0 dBm, and as you can see, the spectrum analyzer, the third order component drops to here, minus 4, about this minus 4 here. So as you can see here, this 3x coefficient here, the slope of this function, is known. So these third order intermodulation products grow 3 times as fast as the usual amplifier. And so there is a theoretical point that is here, which is called the intercept point. I made a video about this concept a few videos ago, so check it out if you're interested. But anyway, this theoretically speaking is the moment where this basically undesired, as you can see here, the undesired third order product reaches the same amplitude, the same power of the main carriers. Okay, so this is the point, and it should happen at more or less 17 dBm, and the output would be, it's just a theoretical consideration. Okay, we're not going to drive the amplifier up to this level. Anyway, this is an interesting point because it gives some information. So typically one takes 17 minus 10, so 10 dB earlier than this intercept point, so at around 7 here, to be the so-called 1 dB compression point. So let me do this, and it is a point in the amplifier where the amplifier is starting to not behave as this ideal line, but is starting to go slower. So at this point it will have lost 1 dB. Okay, so at this 7 dB the amplification will not be 28 anymore, it will be basically only 27. So let me actually check. Let me put the amplifier at, these are theoretical consideration, by the way, so let me see if they are supported by the practice. And here we are getting 33. So 33 minus 7, I guess, is only 24. Is that possible? Oh no, yeah. So, but here we have basically 24, but there are two carriers, right? So the 24 dB is the total power. So we get basically double 24 dBm of power, which is 27 dBm. And so, yeah, it's pretty accurate actually, what we discovered theoretically. And so basically the amplifier is, we already know that by the experiments that we are reaching our 40 dBm level, so 10 watts, at 15 dBm of input, because we checked it before. So yeah, the amplifier is basically following this attenuation curve here. It's basically behaving like that. So yeah, final conclusion about this amplifier: it's a fantastic value for the money. It only costs $22, and as I mentioned, I plan to use it for my AKRF. and yeah, I will definitely report my results, and that's it. Yeah, two last things that are worth mentioning. So definitely, as you can see, um, so let me actually go back to, so let me set again a start frequency of, let's say, 2 megahertz, and a stop frequency of 300 megahertz, so we can see a lot of the spectrum, right? So as you can see, the amplifier creates a lot of harmonics. So definitely it's a must in whatever configuration to follow the output of the amplifier with a low pass filter. The low pass filter will filter out these undesired harmonics that you see there, right? So this is also noted in the manual, by the way. It's completely expected. It is like this for basically most amplifiers. And so this is a little low pass filter that I also bought from QRPLabs, and already made about 1 year ago a video about it. It works very well. So the idea is just to connect it there. But you know what? We can try it immediately just to have a look. Okay, I found it. So I found this adapter. So I can now put in line with the output of the. So let me actually. It's pretty warm now. I didn't realize it. It's very warm. But okay, we were emitting 10 watts for a prolonged amount of time. So okay, and so let's see. Let's have a look. So let's start again. So I'm not sure if it is working as expected. I hope. I haven't tested it for quite a. Yeah, no, I have to, of course, turn on the power, and let's turn on the output. Yeah, so as you can see now, it has filtered out amazingly well all the harmonics. So yeah, this is a extremely nice result. As you can see, we only have our marker is at around 14 megahertz. So let me reduce the stop frequency to 50 megahertz. So we just have our 14 megahertz thing, and the filter has filtered out all the harmonics in an excellent way. So they are invisible 6 divisions, so 60 dB down basically. So yeah, excellent. This is a configuration that can be used to transmit in a very clean way, and I plan to do this with the ACRF, and I keep you informed about my results. Okay, so that's all for this video. I'll see you next time. Bye bye.